Good morning students. Our first chapter in basic mathematics, that is number theory. Name itself says number theory. Here we are dealing with numbers and some basic operations related to numbers. Once again see, I'll start from the beginning, that is number systems. You already studied that in which course. Just recall the number systems. Our first number system is natural number system, and we denote it as n is equal to set 1, 2, 3 up to infinity. Second one is the whole number system, that is w, it's equal to 0, 1, 2 up to infinity. Third one, that's a extended form of the whole number system, that is integers, it's equal to 0 plus or minus 1 plus or minus 2 dash dash up to plus or minus infinity. And the next extended form, that is rational numbers denoted by q. Then q is equal to numbers in the form p by q, where p and q are integers and q is not equal to 0. And next one is irrational number, and it is denoted by caps letter T. Okay, numbers which are not rational, we called it as irrational number. And the last number system is, that is real number system, denoted by caps letter R. Okay, real number system that contains all the number systems. So real number means that includes natural numbers, whole numbers, integers, as well as rational numbers and the irrational numbers. Consider the integers, that is z is equal to 0 plus or minus 1 plus or minus 2 dash dash infinity. Set of all integers. Here see z plus, that represents all positive integers. What are the positive integers? 0 is there. Is 0 positive or is 0 negative? No, right? 0 is neither positive nor negative. Okay, remember this condition. We can't take 0 as a positive number as well as 0 as a negative number. So 0 is neither positive nor negative. That is our mathematical convention. So z plus represents all positive integers. What are the positive integers? Plus 1, plus 2, plus 3 up to plus infinity. Then z minus. What's the meaning of z minus then? Z minus represents all negative integers. It's equal to negative integers. 0 is not a negative integer. So you need to start from minus 1, minus 2, minus 3 up to where? Up to infinity. Clear? Z plus represents set of all positive integers. Z minus represents set of all negative integers. Similarly, you can take q plus. What is the meaning of q plus? Q plus means positive rationals. And what's the meaning of q minus then? Q minus means negative rationals. Okay, symbol itself says na, z plus, plus means positive numbers. Z minus means negative numbers. Clear? Our next concept is even numbers. Okay, then what are even numbers? Numbers in the form 2, 4, 6, 8, 10 dash dash up to where? Up to infinity. We called it as even numbers. And odd numbers. Okay, what are the odd numbers? That is 1, 3, 5, 7, 9, 11 dash dash. We call it as odd numbers, right? Here see, 2 is a positive integer, 4 is a positive, 6, 8 all are positive integers. So we called it as positive even numbers. Okay, Then minus 2, minus 4, minus 6, minus 8 dash dash dash. We called it as negative even numbers. Okay. By this you can say that even numbers does not imply only positive integers. Even numbers means plus or minus, but that numbers in the form 2, 4, 6, 8 or minus 2, minus 4, minus 6, minus 8. We called it as even numbers. Then observe here, plus 1, plus 3, plus 5, plus 7, plus 9, plus 11. All these numbers are positive numbers, right? So we called it as positive odd numbers. Okay. Then how to write negative odd numbers? That is minus 1, minus 3, minus 5, minus 7, minus 9, minus 11, up to where? Up to infinity, right? Infinitely many numbers are there. So all these are negative odd numbers. Okay, clear? Remember the condition. Even numbers and odd numbers means it is only positive numbers. Even and odd numbers means you may take positive numbers as well as negative numbers. Next is prime number. Okay, one of the important number system. Any integer p greater than 1 is said to be a prime number if it has no other divisor except 1 and itself. Okay, any number, any integer greater than 1, okay, is said to be a prime number. Then it has no other divisors except only two divisors, right? One is the number 1, another one is the itself. Okay, so condition for prime number is that number must be greater than 1. Okay, second condition is divisors of that number is 1 and p itself. Okay, just remember the condition. Any number is said to be a prime number, that number must be greater than 1. Second condition is that number is divisible by 1 and by itself only. Okay, for example, see 2. Okay, check whether 2 is a prime number or not. Clearly 2 is greater than 1. Then tell me the numbers which divides 2. One number is 1, right? 1 divides 2. Next number is 2 divides 2. Is there any other numbers which divides 2? No, right? So 2 is divisible by 1, 2 is divisible by 2. There is no other number which divides 2. So observe clearly, first condition holds, right? Number is greater than 1. What's the second condition? Divisors. That means only two divisors you can see, right? One is the number 1. Another one is, see, 2 only, right? Because your prime number is 2, right? See, 2 only divides that number. So 2 is a prime number. Then what about 3? Check. First condition is 3 is greater than 1. Condition holds, right? That number is greater than 1. What's the second condition? Divisors of 3 is 1 and 3 itself. Check. 3 is divisible by 1 and 3 is divisible by 3. Other than 1 and 3, is there any number which divides 3? Just check. No, right? There is no number which divides 3 other than 1 and 3. Therefore 3 is a prime number. What about 4? Check. 4 is greater than 1. Okay, first condition holds. Tell me the numbers which divides 4. First number is 1, right? 1 divides 4. Then 2 divides 4. Then 4 divides 4. Here see, other than 1 and 4, you are finding one more number, that is 2. Okay, that fails the condition. What is our condition? Number is said to be a prime number. Divisors of that number is 1 and that number itself. but here we are finding one more number which divides 4. Therefore 4 is not a prime number. Then take the number 5. Then see, 5 is greater than 1. Divisors of 5 are 1 and 5 itself. Then you can write 7. Then check 9. It's a very important case. Is 9 is a prime number? Check. First condition is 9 is greater than 1. Okay, your number is greater than 1. First condition holds. Then tell me the divisors of 9. First one is 1. 1 divides 9. Then 3 also divides 9, right? 3 3s are 9. Then 9 is divisible by 9. Now see the second condition. If 9 is a prime number, divisors of 9 are 1 and 9 itself. But here see, we are finding one more divisor, that is 3. Okay. Therefore 9 is not a prime number. Okay. So next number is 11, 13, 14 is not a prime number. 15, again 15 is not a prime number. Why? 15 is divisible by 1, 15 is divisible by 3, and 15 is divisible by 5, and 15 is divisible by 15. Now here you can see two other numbers are there, right? One number is 3, another number is 5. Other than 1 and 15, two more numbers are there. So that fails our condition. Therefore 15 is not a prime number. So next number is 17. I think now you are clear. Just remember the condition. Any number is said to be a prime number. First condition is that number must be greater than 1. Second condition is divisors of that numbers are 1 and that number only. Any number which divides the given number, then that is 1 and that number only. Then we call that type of numbers as prime numbers. Okay. Next is composite number. Okay. So very simple definition. Numbers which are not prime. Okay. Then we call that numbers as composite numbers. For example, see 4. 4 is a composite number. Then what about 6? 6 is composite number. 8, 9, 15 or 10, all these numbers are examples for composite numbers. Why? Because these numbers are not a prime number. Numbers which are not prime, we call that numbers as composite number. Then very important note is 0 is neither prime nor composite. Okay. We can't take 0 as a prime number, or we can't take 0 as a composite number. 0 is neither prime number nor a composite number. Second observation, 1 is neither prime nor composite number. Okay, clear? Okay, so by this you can say that 0 and 1 is neither prime number nor a composite number. Our next concept is fundamental theorem of arithmetic. You may study this theorem in your lower classes. Once again, see, this theorem says every composite numbers can be expressed as product of prime numbers. Okay, this is a fundamental theorem. Okay, take any composite number, you can write that composite number as product of prime numbers, and this decomposition. Okay, what's the meaning of decomposition? Means this expression, okay, is unique. Okay, this is a fundamental theorem. one composite number is given, you can write that composite number as product of prime numbers, and that expression is unique. For every composite numbers there exists only one such expressions. Okay, that's the meaning of unique. Okay, for example, see, take one composite number. I'll start from the lowest number. Suppose I'm taking plus 4. We know 4 can be written as 2 into 2. We know 4 can be written as 1 into 4 as well as 4 into 1. Then why I am taking 2 into 2? Because theorem says composite numbers can be expressed as product of prime numbers. While writing the product, you need to take a prime number. See, here 1 and 4 is not a prime number. Here also 4 and 1 is not a prime number. Therefore, this decomposition is not possible. While taking the decomposition, you need to take only prime numbers. That's why I am writing 4 is equal to 2 into 2. Okay. So, or you can write 4 is equal to 2 square. Okay. 2 times 4. Take the next number, that is 6. How to write 6 in terms of prime numbers? You can write 2 into 3, or it is same as 3 into 2, right? Commutative property, 2 into 3 is 6, as well as 3 into 2 also is equal to 6. So, 6 is equal to, you can say 2 to the power 1 into 3 to the power 1. Okay, that means 1 time 2 and 1 time 3. Now consider some bigger numbers. I am taking 16. You know 16 is not a prime number. Clearly 16 is a composite number. Now 16 is equal to, okay, now decompose 16. I will start from least prime number, that is 2. 2 8s are, 2 4s are, 2 2s are. Okay, so 16 can be written as 2 into 2 into 2 into 2, 4 times 2. Or you can write 16 is equal to 2 to the power 4. Okay, now consider the next number, 25. Okay, in this case clearly 25 is not a prime number. Then 25 is equal to, decompose 25. Start with 5, 5 5s are 25. Okay, so you can write 25 is equal to 5 into 5, it's equal to 5 square. Okay, now see, here also product of prime number is there, here also product of prime number is there, here also product of prime number is there. That is our fundamental theorem of arithmetic. Take any composite number, we can write that composite number as a product of prime numbers.